Hi, I'm Professor Goins. Welcome to the Math Professor's YouTube channel. We create videos on topics found throughout college mathematics, ranging from algebra through calculus and more advanced classes as well. If that's something you're looking for, please consider subscribing and watch some of our videos. That really helps us with the YouTube algorithms and spreading our videos. Let's get into the current one. What I want to take a look at is called the nth derivative test. So let me sort of set the scenario. You know that the second derivative test is a tool used to classify critical points as local maximums or local minimums, and is much quicker than the first derivative test. And sometimes the second derivative test, however, is inconclusive, where the second derivative is a value of 0, then it does not tell you whether it's a maximum or a minimum. Does the story stop there? Well, it does not. So we can actually keep evaluating subsequent derivatives, and get a conclusion based on those results. So let's see what happens here. First and foremost, suppose a function f of x has critical point x equal to a, but the second derivative at a is 0, meaning that the second derivative test is inconclusive. Here's a very simple example illustrating when that happens. If I look at the function f of x to the fourth, which, remember, it's not a parabola, but it still has a sort of parabolic shape to it, clearly then has a minimum at 0. Well, the second derivative is 12x squared, which when I plug in 0, I do get 0. So even though this is clearly a minimum at the critical point, the second derivative test is inconclusive. Well, let's see what we can do to expand upon that. The nth derivative test says the following. Suppose f of x has a critical point x equal to a, and n is the smallest integer for which the nth derivative evaluated at a is non-zero, and f is at least nth order differentiable, then what can we say? If n is even, so like you have the second derivative, the fourth derivative, the sixth derivative, whatever the case may be, it's an even order derivative. If it's positive, then it's a local minimum. If it's negative, then it's a local maximum. If the order of the derivative is odd, then we have an inflection point. Okay, so let's see in practice how this works. Let's start with this function right here, the f of x to the fourth, which again, clearly 0 is a minimum, but let's see how the nth derivative test applies to that. F of x is x to the fourth. Let's classify the critical point x equal to 0. So what this says, I just have to compute a derivative, plug in 0. Compute a derivative, plug in 0. Repeat that process until the result is non-zero. Let's see what happens. First derivative, 4x cubed, and the first derivative at 0 is 0. Second derivative, 12x squared. Second derivative at 0 is 0. Third derivative, 24x. Third derivative at 0 is 0. Keep going. Fourth derivative, 24. Fourth derivative at 0 is 24. So I keep repeating this process. Differentiate, plug in the critical point. Differentiate, plug in the critical point, until I get to a value where this is not 0. Now let's look at our conclusion. What is the order of n here? Well, the order n is 4, meaning it's even, and the 24 is positive. So let's look at the case down here. N is even, the derivative is positive, therefore it's a local minimum. Which clearly we knew it was a local minimum. Let's do another fairly obvious one, and then we'll do another couple after that for more complicated functions. Consider the function f of x is equal to x to the fifth. Okay, x to the fifth has a shape that looks like this. Sort of like the cubic function. This is going to be a little more extreme, a little higher. I don't want to use the word stretched. It's not necessary. That's not really a stretch. But it looks sort of like the cubic function. Clearly x equal to 0 is a critical point, and clearly it's an inflection point. But let's see, because the second derivative test is inconclusive for that critical point. Let's run through the computations to make sure we see how it matches up with the nth derivative test. Okay, so again, differentiate and plug in. So differentiate, get 5x to the fourth. First derivative is 0. Second derivative, 0. So again, second derivative test is inconclusive. Third derivative, 0. Fourth derivative, 0. Fifth derivative, 120. Therefore, the fifth derivative is 120. And in this case, n is odd. So n being these n equals 5 is odd. N equal 5 being the smallest integer for which the derivative at the critical point is non-zero. If I look over here at my possibilities, n equal to odd says we have an inflection point. Now, this was a little bit overkill to show that 0 was an inflection point for x to the fifth. We know what the graph looks like. We can show that the second derivative is positive and negative on either side of that value. However, if I have a significantly more complicated function, the nth derivative test would be useful in that scenario. So let me clean this side. I want to leave the statement of the test up here. Let me go ahead and clean the right-hand side, and then we will take a look at a more complicated function. So you can verify on your own, but show that x equal to pi is in fact a critical point of this function. What I want to do is let's use the nth derivative test to classify it. Just like the previous examples illustrated, we differentiate, plug in pi, differentiate, plug in pi. We just continue that process until when I plug in pi to a subsequent derivative, I get something that's non-zero. We look at both the order of the derivative and the value, or in particular, the sign of the value of that derivative. And if it's positive or negative, even odd, that tells me my classification. Let's go ahead and start computing derivatives here. Well, first and foremost, as far as differentiating this, If you're watching this, chances are you're in Calc 1. So let's decompose this function. Let's look at the structure of it. I've got a product of two functions, product of sine squared and cosine. That means I'm going to have a product rule. My first factor is also a composition, which means I'm going to use a chain rule in this one. When I differentiate this factor, we'll use the chain rule. So let's go ahead and differentiate. The derivative of sine squared would be 2 sine cosine. And then I also have the factor of cosine here. And then plus sine squared x times negative sine x. We'll have to differentiate that. So let's clean it up and then we'll evaluate it. This would be 2 sine cosine squared minus sine cubed. So again, this is the first derivative. Plug in pi. Sine of pi is 0 and cosine of pi is -1. This term has a factor of sine, this term has a factor of sine, therefore the first derivative at pi is 0. That just verifies that it's a critical point. Okay, we certainly have to go farther than that to use the nth derivative test. This just verifies that it's a critical point. And chances are the second derivative will be 0 as well, because otherwise the nth derivative test is overkill. If the second derivative is 0, then it just verifies that the second derivative test is inconclusive. But let's check it out. The second derivative, let me sort of section that off. The second derivative, okay, so differentiating this, I get 2 cosine squared plus 2 sine times 2 cosine times negative sine. Okay, so that is the derivative of this first part minus 3 sine squared times cosine. And let's go ahead and clean that up. We get 2 cosine cubed. 2 and 2 is 4 minus, so minus 4 sine squared cosine minus 3 sine squared cosine. And I think I spoke too soon. It looks like the second derivative is non-zero, which means, well, first of all, let's go ahead and plug it in. Second derivative at pi, if I plug in pi, cosine of pi is -1. -1 cubed is -1, so that's -2. But then this term is 0 and this term is 0. And now the order of the derivative is 2, so n equals 2, which of course is even. And the second derivative at pi is negative. So what does that say on my conclusions over here? The order is even, so it's one of the first two cases, and the second derivative in that case was negative. Therefore, we know that pi is a local minimum. So really the second derivative test was conclusive in this particular example, but we still followed the same procedure that we would for any other function using the nth derivative test. Differentiate, plug it in, differentiate, plug it in, until I get to something that's non-zero, and then I look at the order of the corresponding derivative, the sign of that derivative value, and then I use my chart over here. So hopefully that's helpful for using the nth derivative test. Once again, if you find these videos useful, please consider subscribing, and thank you for watching.